that for each of them there are interesting ways of proving what is the right thing to do. And for plus, essentially, you send the gradient to both branches. For the max, you send the gradient to whatever is the maximum guy at that particular point. So max becomes a router of the gradient. Plus becomes a splitter of the gradient, but it's not really a splitter. It splits and sends the gradient in both directions without reducing its value, right? So, so I come here. Essentially, I'm sending this gradient both here and here, and I continue essentially this way. And then of course here I come here. This plus will again get 0.20, 0.20. You see what I'm saying? So I will stop at just basically, my point in doing this is not to get you to write this program, but to get you to understand that this is done mechanically. In particular, actually, if you look at this, if you could actually have written this whole block, remember one of the other things that computers do is they do block structuring. You could have written the sigmoid function, the sigmoid gate, the entire sigmoid gate as one single gate. And then say that's a simple operation. They're called 1 by 1 plus e power minus x. And remember I told you what is the differential of 1 by 1 power e power minus x. If g of x is 1 by 1 plus e power minus x, then the differential is g of x times g of 1 minus x. Just like once in your life you figured out that derivative of 1 over x is minus 1 by x squared. Similarly, once in your life you figured this out, so that becomes, now this block now can essentially, you say I'll put this, the gradient comes here, the gradient comes out just by putting in directly g of x. Because, g dash of x is g of x times g of 1 minus x. Do you see what I'm saying? This is what actually made the computation part of neural networks very easy to some extent. That gets us to, so basically actually it even shows that in fact, if you just did you could either have done this in the costly way, the way we did it earlier, or you could have plugged it in 1 by g of x times 1 minus g of 1 minus x, and 1 minus g of x, and that would also give me the same exact number. That's because math works, unlike computers once in a while. But so that was there, right? So the patterns in Blackboard Flow, actually, as I said, the multiplication is more complicated. I won't talk about it right now. You can read it in the Andres write-up. The max is essentially a router. In this particular case, this is 2. So you came up to here, and this is 2, this is minus 1. The max of 2 and minus 1 is 2. So all the gradient goes just that direction. And the plus is a splitter. This is what happens. If you look at the autodiff, it doesn't at all look like what you learned in grade school. But how many times, how do you think computers actually do multiplication? The way humans do it? Like we put big number in terms of big number and write multiple layers and take the carry out, etc., etc. No. Once you figure out the concept, you can re-implement it in a way that is better for computers. That's what we wound up doing here. Okay. Now that brings us to why Jensen Huang is the happiest man. Jensen Huang is who? He is the CEO of NVIDIA, which was an also-ran chip company. Intel used to be the only thing, and then Motorola used to be there, that died. And NVIDIA used to generally hang around. They had not much going for them. AMD was making computers. And NVIDIA said, hey, we'll make graphics processing units, right? And that was mostly for the screens, basically, because each pixel has to be separately handled. And so it required a huge number of dumb CPUs. These CPUs don't have to do much other than just multiplying, adding, and then throwing the number out. And those are like, so you have normal CPUs, you have the multi-core CPUs, and you have GPUs, which are humongous core dumb GPUs, dumb CPUs, which was mostly only used for showing stuff on the screens. And gamers were happy. But then even gamers, unfortunately, if you don't know, I don't know, there are like 2 or 3 people who make money on gaming. The rest of the gamers are losers. They don't have any money. They don't have any money. So who is going to buy these big GPUs, right? And so almost NVIDIA was going out of business, and then came right in time this connection between doing this kind of brain dead operations, multiple of them, and AI, or what people call AI, which is being able to do image recognition. And so Jensen Huang, like any good capitalist, said, who said we were in gaming industry? He says, always been known that we are an AI company. He has never probably, he went to Oregon State University, Tom Dietrich is there. I'm pretty sure he never did an AI course. Who cares, right? But now he's an AI guy, and his company is an AI company, and they basically sell GPUs, right? Okay, they basically sell GPUs, and rest is history. And the reason GPUs make sense is because this is, again, you might argue that this might actually be the only similarity neural networks have with brains, because individual neurons are pretty darn stupid. They are bidirectional. They are less stupid than the individual neurons of the real neural networks, the computer neural networks. But they don't do like, let's just write Hamlet. There is no Hamlet writing neuron for you, right? Okay? So individual neurons do very simple operations massively parallelly. This is what GPUs are actually also doing. Okay? So we will stop here. We'll continue.